good friend and research partner, Jason Dittman, who's now at CFA, Harvard. Actually did a presentation on a different system a couple of years ago. And we've had about 80 nights for this project. This is just a small sample. This is a sample of what we've done 3 of those nights. But it is one of our most recent and most interesting papers. So, planet transits happen not infrequently. They do happen quite a lot. And in fact, you can see that happen in our own system. This is an actual NASA image from the SOHO's solar observing satellite of Mercury actually going across the sun. You can see multiple exposures here as Mercury moves across. And this is basically what we're observing in other solar systems, except for we can't actually resolve stars like this. All we see is a point of light. So what we look for is a change in brightness when this planet blocks out a little bit of the sun's light, the star's light. And that's sort of shown schematically here. We have the planet when it's not eclipsing the star. We have just a constant brightness of the star. And as it goes in front of the star, you can see dip. This dip is usually 1 or 2%, depending on the ratio of the radii between the star and the planet. And we can actually use this to measure physical properties of the planet and actually start speculating about structure, which is really cool. We started doing stuff with maybe planetary sciences in the near future. And another nice thing is that we can also time these events very accurately, down to minute or second scales. So this particular case is a very unique case, actually, in transiting planets. There were 2 independent discoveries, Bakos and West. They published about a week apart, and they agreed on this common name. That's about all they agreed on. There is plenty of disagreement with the radius, about 14% disagreement with the actual planetary radius, which is huge in this field. There's disagreement about the actual type of star it's orbiting, which is a lot of the reason for this radius disagreement. A lot of people say that you only know your planet as well as you know the star. That's very, very true in this case. And just generally a lot of disagreement between these 2 teams, which is pretty much never been seen before. It just makes it a very interesting project. So we wanted to look, and the motivation for this project in particular was just to look at what's going on in the system, what's the actual case. Our secondary motivation for our overarching project is to look for timing variations, TTVs, transit timing variations, in the system, which might indicate the presence of additional planets. Maybe an additional planet is tugging on the first planet, and that makes its period slow down a little bit. So this is our telescope we use. This is a 1.55 meter, 61-inch Kuiper telescope. It was built, I believe, back in the late 50s or 60s to survey the moon for Apollo missions. I've been up here probably about 80 times now. I know just about every function of this telescope right now. It's an enormous headache, but we do get a lot of good science out of it. We observed this particular transit 3 different times, once in September and twice in November of 2009. And for all these observations, we use the same camera, same setup. We use the Montreal 4K CCD with Arizona iBand, which is a custom later. One ask question about that. Write that down and ask me about that later. But we took images every about 30 seconds, which gave us 1,380 actual science images to reduce. And so to deal with that, and all of this gigantic flood of data we've had from our other of the 80 nights, Jason and I actually built over the last year or 2 an IDL pipeline, which takes in our raw data and our calibration frames and spits out basically this. We've massaged this a little bit so that to take out a couple of systematics. But this is actually the data we get out from our IDL pipeline. This is the last night on HAT-P-10-WASP-11b. It's quite high quality data. You can see the dip is about 2% here. This is the percent scale, relative flux. And we have low amplitude RMS. So basically, when we run this through our pipeline, what it spits out is this plot and a file which generates or gives us all the parameters that we're measuring. The ratio between the stellar radius and the planet's radius, which is very important. The center of transit time and the orbital inclination. So to analyze all this stuff, we basically looked at that file and compared it to what other people were saying. And we stacked up all three of our transits on top of each other. We also took all of the transits that have been observed, at least the ones that we've had access to, and we plotted them on this diagram here. Just for, this is timing difference, and this is epoch, which means the orbit of the action. What we found, basically, is that we agree very well with West. We agree within 1 sigma for the radius ratio, which means that we're seeing the same amount of light being blocked by the star. We disagree with Bacchus, which is kind of strange. We don't really know why that is yet. But we actually looked at both of their papers and we decided to use the Bacchus stellar models because they had complemented Keck, which is very high quality data. We're pretty sure they got their stellar models right. So when we combine our radius measurement with the Bacchus stellar models, we get a radius of about 0.995 Jupiter radii. It's about the same size as Jupiter, even though it's about 0.46 Jupiter masses. It's very puffed up, which is relatively normal for these planets. They're heavily irradiated, which means they're hot, they're less dense, as we were talking about in the last lecture. In fact, less dense things expand. This, however, it's a little bit too dense. Our radius is about 10% smaller than models predict. Models basically predict without a core, this planet should have about 1.1 Jupiter radii, which should be a little bit bigger than Jupiter. Our observations are showing that it's a bit smaller, about 10% smaller, which means it's about 35%. That's so what does that actually mean? That means probably that it has a dense core that the models were including, maybe a big rocky core inside with a large envelope of gas on the outside, which is very interesting. It's the first time we can really start speculating between exoplanets and planetary science. It's a really new sort of emergent field. I'm very excited about it. And additionally, when we looked at all three of our transits together, we find absolutely no evidence for timing changes. They're consistent to within a second, which is a lot better than even our error bars can do. So we're seeing no evidence of big, heavy, nearby planets in the system that perturb the first planet that we already know is there. That doesn't mean that there's not other planets in the system, it just means that there's no other big ones nearby. Well, this is just a summary of basically what I just said. We found the new radius, which is very suggestive about the structure, and hopefully we can start actually, I'm starting to think about implications for the atmosphere and structure of this planet. And we find absolutely no evidence of timing. And hopefully the next two talks will talk about timing variations.
What kind of stellar parameters, uncertainty in stellar parameters, the result of uncertainties you're thinking about?
Yeah, so a really big one. There's a huge, about 100 Kelvin disagreement in the equilibrium temperature. That's because I think one of the papers has the star, they said it was a K3 volts, and the other one said it was a K5. And that's a difference in stellar surface temperature. And that'll definitely affect how big the planet is, certainly.
What kind of observations you need in order to stellar?
Yeah, so we need high quality spectra, and I think they have that. I think the Bacchus, the Keck data actually got that. They had a whole huge detailed section in their paper. It's several pages, very difficult to read. But I think it does make sense.
So from your timing data, I know it depends on both mass areas. If we put a limit on what the most massive at a certain distance,
yeah, absolutely. We can certainly say there's no Jupiter-sized or bigger planets anywhere nearby within a couple of years. We haven't actually done the simulations for that, but I mean, at a low level sort of approximation, we can certainly say.
How sensitive are your results to any uncertainties in the orbital elements, such as the inclination of the orbit?
I'm not sure what you mean.
Well, when you're determining an orbit, you know.
Oh, yeah, so we do measure orbital inclination.
Right.
Which is sort of, it's very degenerate with the transit duration. So you can imagine if the inclination angle, so you have a star here, if you have an inclination angle like this that crosses the star at a different latitude line, you're going to have a much shorter transit. So, in fact, we've been thinking Jason and I have talked a lot about this, that there are a lot of hidden systematics in measurements like that people just are not seeing yet, because this is a relatively new field, and we're actually kind of worried about it.
What about the ring system for shooting?
So ring systems, it would broaden the transit a little bit, depending on what its optical properties were, if we could see it, because we're in the eye band here. I don't really know. I mean, if you had a bunch of ice and rock out there, it would certainly pop some light. And it would make the planet a little bigger, as long as it's in a certain inclination of the planet, yeah. I mean, we thought we saw a ring system in one particular observation. That's a long story, and it's almost certainly wrong. I don't think anyone has definitively observed the ring system, and I think it would be extremely hard to, because relative to the cross-section of the planet, if you just take the cross-section of a ring system at any given inclination, it's going to be very small. So it'll be a small signal. It'll be hard to observe. I'm not saying it's impossible to observe, but it would be very hard to actually figure out if that's the case. That's all I have to do.